Good morning, everyone, again. Distinguished guests, professors, researchers, students, and friends of Koç University. Welcome to the Koç University Quantum Summit. It's truly a privilege to host some of the brightest minds in quantum science here on our campus. Scientists and thought leaders whose work is shaping not only the future of technology, but the way we understand the world itself. Quantum physics, as you know, is full of paradoxes. Particles that are waves, things that exist and don't exist at the same time. And maybe that's what makes today so exciting. We're all here in one place at one time to make sense of a world that sometimes seems impossible to define. But what isn't uncertain is the power of science. In a world that can feel unpredictable and divided, science brings people together from different countries, disciplines, and institutions to collaborate, question, and create. That's the true spirit of this summit. So we're very proud as Koç University to be hosting this gathering during the International Year of Quantum. Over the course of today, you'll hear from some of the world's most influential voices in quantum computing, sensing communication, and cryptography. Today's sessions will explore the foundations and frontiers of quantum research. Once again, thank you all for being here and for sharing your knowledge, your curiosity, and your time with us. And now, to officially open the Koç University Quantum Summit, I would like to invite to the stage our president, Professor Dr. Metin Sitti to the stage. Thank you.
Thank you. Good morning, everyone. It's my great pleasure to open today's summit. So, as you know, the quantum technologies is a very important field these days, more and more. So I will not read and talk, but basically, as you know, this year is quantum year. And we know that also just the Nobel Prize this year in physics is also given to quantum mechanics research at Berkeley and other places. And as you know, as the top research university in Turkey and the number one, let's say, by our Higher Education Council criteria, we are highly interested in creating research-focused fields. And we have been discussing this since 2 years I have been here, and quantum technologies is one of them, naturally. We have discussed AI, we have the healthcare, and many other areas that our university is very strong. And also, thanks to our physics department and also engineering, we have also great people in the campus studying and doing research on quantum technologies. As you know, quantum technologies is not anymore just theory, and there are more and more technologies coming up in communication, computing, and sensing. I myself work on nanodiamonds that are amazing MRI contrast agents, and we use them in our micro robots. And again, this year, everywhere is celebrating this important quantum year, and this kind of summit is very important activity to get together, see what's the state of the art developments going on, and discuss where we can go and how Koç University and Turkey can position itself in this very important research field. Because also, since 2 years, I've been emphasizing that our research should not only lead in Turkey, but we should lead in the world. So the question is, tomorrow especially, we'll have more internal discussions how our university can position to create research in this field to become one of the world leaders. Also, as you know, science is so important these days for unifying everyone, where we have now more and more fragmented and polarized world. And I hope this kind of summits will get us together as engineers, physicists, and I see here even medical doctors and all different disciplines here today. Thanks for coming. Also social sciences and even international relations and many other fields from our campus, so that we can discuss how quantum science and technologies are exciting and how they will form our future in different aspects. So also in my research, one of the first discoveries was gecko lizard adhesion. If you know these lizards climbing on the walls, they have these tiny nano micro hairs. And we discovered that they were using van der Waals forces to stick to every material. that we can envision, and the reason was quantum physics. It was using van der Waals forces, as you know, which exist as a weak force for every atom, but such weak force, if you have many tiny hairs, they can create very strong forces to stick almost any material. That created now a new adhesive technology. So I'm very happy to see very distinguished speakers coming today all the way from different parts of Europe. I'd like to mention them briefly. As you know, I was also director at Max Planck Institute, and I had the great pleasure to know Professor Gerd Leuchs. He is the indeed founding director of Max Planck Institute for the Science of Light, and he's currently director emeritus there. And he has been very influential on the foundations of quantum optics, and he has inspired a lot of generations of scientists, including many here at our university. Also, Professor Mauro Paternostro from the University of Palermo and Queen's University Belfast. He is a global leader in quantum information and thermodynamics, exploring the mysterious transition between the quantum and classical worlds. Also, we have Professor Luis Sanchez Soto from Universidad Complutense de Madrid, and I think he's also director in Max Planck Institute for the Science of Light, a brilliant theorist bridging fundamental principles with real-world applications. Also, this afternoon, unfortunately, he cannot come in the morning, Professor Metin will join us. He's the head of the Cavendish Laboratory at the University of Cambridge, which is one of the most influential voices in quantum optics. And also, he received recently our prestigious Koç University Rahmi Koç Medal of Science. So we are truly privileged to host all of these privileged guests and all of you here today. And I look forward to hearing many interesting discussions. But before that, I'd like to also thank the organizing team, especially Professor Özgür Müstecaplıoğlu, who has been leading quantum technologies and science field in our campus, and also his team in the College of Sciences, and also our Vice President for Academic Affairs, who is delayed because of flight issue. She will join us in the afternoon. So thank you all for organizing such important summit today. Again, I look forward to seeing exciting discussions and engagement from everyone, and I hope we have plenty of time for discussions. And once again, welcome to our university, where the science and creativity and curiosity meet here. And this is a very specially designed campus with knowledge of science is indeed is one of our gate name. So in that sense, yeah, I wish you all a successful and fruitful summit today. Thank you all for coming.
Thank you, Professor Sitti, for your opening remarks. And now here is someone, as Professor Sitti already mentioned his name, but I do want to introduce you. Someone who has not only advanced quantum science in Turkey, but has built an entire community around it. Professor Özgür Müstecaplıoğlu from our own university leads the Quantum Enabling System Technologies Group, aptly named QUEST, because quantum science is indeed a quest for deeper understanding. So please welcome Professor Müstecaplıoğlu to this stage.
Thank you so much. So I would like to welcome you all to our beautiful campus, and I would like to thank our president for supporting us all this process, and our distinguished speakers today, as well as all of our esteemed guests. And I see a lot of friends from academia as well. Welcome. And of course, our wonderful students, some of them are still helping over there. So thank you all for coming and joining us today. Well, to me, it is like quantum, like this organizing such an event is a sort of a miracle. So I would like to thank all the people that helped throughout this organization. Funda Hoca currently not here, but hopefully will join us in the evening. And this team made it realize this conference, so thank you all. So I would like to today basically give a short presentation. Normally when I start to talk, I come to the point after an hour, but today I have wonderful speakers, so I will leave the scene to them. I will just mention what we have done here at the Koç University and what we have currently regarding and related to quantum physics. So we have 5 centers, and you can be wondering how they can be related to quantum physics, but the technologies that you are going to hear today, we will have demonstrations from algorithmic as well, optimization, AI, and the applications of them to materials development and communication and computing. They can be relevant to many centers. So all these centers are strongly related, basically, our approach in quantum research. Then we have a very good young faculty here doing experiments in integrated photonics, single photon sources, photon detection. Their laboratories, some of them Professor Gerd visited yesterday, are also very relevant to quantum research. And we also have other, maybe not directly, that it is called the second quantum revolution, but still very closely related disciplines and very strong laser and photonics groups with the experimental facilities here as well. So we have strong infrastructure for quantum physics and also some theory groups and strong collaboration between them. We are working with industrial engineering, Barış Hoca, in hybrids and quantum-inspired algorithms. And I would like to thank and also mention that our wonderful students are working in different aspects of quantum technologies in our quest group. So we organize a lot of events, especially this year in the year of quantum. For instance, we also celebrate every 14th of April, the H Day or Planck Constant Day, Quantum Day. And we usually receive some feedback from the participants that after all these infrastructures and the nice faculty and events, why not to have a master's program or graduate program in quantum physics or quantum technologies. And we are taking some first initial steps for that. We have started a quantum education program, a quantum track program, technologies and photonics included in our College of Science. So I'm happy to announce this. Then we are also looking at not only from technological point of view, we have very active Office of Sustainability, which is a very important aspect of quantum physics and the more correct development of quantum technologies and learning from mistakes in the past. Maybe we can build a better technology, more green technology. And for this, we established a web page, trying to update it regularly on sustainability aspects of quantum technologies. Then we are also organizing some panels similar to like this April panel, but we also established these panels with different institutes in Turkey, like TÜBİTAK, ULAKBİM and their computational center. Again, not only exactly on quantum technology, but how they touch to society, what they have from the ethics point of view, law point of view. So we try to bring a community together, not only physics or engineering, but different social science communities as well. So we also have some far outreach activities. We organize public talks to community. This is a talk at Sarıyer Municipality. Then we also have very nice summer schools. Our beautiful campus offers a very good experience to young students, even at high school level. We offer them at different levels, quantum programming, quantum biology courses that can be accessed by undergraduates and even high school students. Well, this year we dedicated science fair to quantum theme. So we organized some quantum games, quantum theme park, quantum treasure hunt. We just had some very delocalized and nice activities at science fair. And this was another activity that we have done, some poster prizes as well. And our students here in summer, they are very busy, of course, but thanks to them, we can also contribute other events and promote Koç University to different circles and different students in the country. So we have some science villages. People go and stay in tents. It's a very different environment. So just curious students come and listen to quantum physics in this very interesting environment in different villages in the nation. Then we also have some collaboration with other universities. Burçin Hoca is here. He's organizing some impact of how to train high school students and teachers on quantum physics, because there's a discussion in the world how to make K-12 to Q-12, how to transform abstract quantum concepts even at high school level. So we contribute these events as well. So we have also presenting some consultation and awareness talks to policymakers, or institutions in the country. And we are also organizing some documentaries even for elementary school students. So with our national television, we made some science communication projects, how to teach quantum physics to even very early ages, using only by videos or some nice allegories and that kind of different science communication methods. And this has been listened by some little kids, and I got some interesting feedback from them. And we also have some discussions of how different sectors can be impacted by quantum technologies. So especially AI, due to energy constraints, can benefit from new quantum technologies. So we distribute some talks and gave some panels and talks on how AI can be reshaped by quantum technologies as well. And one of the biggest events here is Hobbit, which is our first and international conference, and Mauro was one of our usual suspects here. Thankfully, he supported us there. So we organized that international conferences also together with my students here. And Professor Shimowski was the person who is responsible for what I am today. So he was my supervisor and brought me to the quantum optics wonderful world. So today we're also enjoying another event, another conference, and I would like to say that they will tell you today wonderful promises of quantum technologies, but also enjoy the ride. This is not only the end of the journey, but the journey will itself be illuminating. So we are going to hear good illumination from them. Thank you for being with us. Thank you.
Thank you, Professor Müstecaplıoğlu, for sharing with us what's happening at Koç University when it comes to quantum technologies. So we're going to first start with our distinguished speaker, who truly embodies the spirit of light, quite literally. Professor Gerd Leuchs is one of the world's leading figures in quantum optics, Director Emeritus at the Max Planck Institute for the Science of Light, and President of Optica. So please join me in welcoming him to the stage. He's going to come with his computer. We're going to help him.
Yeah, thank you very much. It's a great honor for me to be here. I should say I was president of Optica last year. Now this is my last year in the board of Optica, and the title is immediate past president. Okay, so that's so I came here day before yesterday in the evening. So yesterday I had the opportunity to look at some of the groups, and I know this was only a fraction of what you do here in the field, and I was very impressed. And I saw you have very engaged and motivated young people, which is very important because the young people are our future. So congratulations to have such nice activities. Now, I was asked to give a talk to people who are not at all in the field, who may not even be in science. So to all of you who know more, excuse me, excuse the level that I will be talking of, but maybe it will at least be a bit entertaining. So it's about quantum science and technology, and we already heard that this is a hot topic. The European Union some years ago established a flagship, and now if you're not so close to quantum, you can ask what is special about quantum. And it was already said in the introduction that there's all this this aspect with quantum physics that something is a bit strange, it's a bit weird. And so on the first slide, I wanted to emphasize that what we do in physics, we observe nature, we try to explain effects by tracing them back down to some fundamental principles. For example, the gravitation, the equivalent for electrical charges. This is the Coulomb law. And when we do quantum physics, there may be a new fundamental law. The fundamental principles, they cannot be deduced. So there is a limit to, at least up to this point, to where we can ask questions. So you can, if you look at the motion of stars and everything, so can all be traced back down to the fairly simple law of gravitation. But when you say, why this law of gravitation, then nobody can give you an answer. So you could also say, this is weird. Where does this force come from? There's nothing between these bodies. Why are they attracting? So we say, okay, we observe nature, we know it's there. So there's always this limitation. And in quantum physics, we see behavior that reminds us of waves, and we can use our intuition from water waves. But there's one additional thing, or at least one important additional thing, and this is what happens in the quantum measurement process. And so people struggle. People came up with different interpretations of quantum physics that deals with this aspect, what happens in the measurement process. And so you can go to conferences where the representatives of favoring one or the other interpretation, they fight. But when they do calculations and predict outcomes of results, they agree. So I think it is, again, a fundamental principle, what happens in the measurement process. And I will come back to this because it's so important. So in quantum physics, we have something we call superposition. This is we have mathematical solutions, and we can go to linear combinations of them. This you can always do when you have waves. This is nothing special for quantum. Then there is the observer effect, what happens when you do a measurement. This is especially quantum. And then you can have this notion, what is called entangles. This is when you have a composite system. There's a very special correlations, which is partly superposition, which is not quantum, but together with this observer effect, it becomes a very interesting quantum feature. So my plan for today are two things. So this is addressing those of you who are not so close to physics. I was thinking, if I really want to be successful with my talk here, I should convey something to you that maybe 2 weeks from now, if someone asks you, you have been at this quantum summit and there was this introduction to quantum physics. Do you remember anything of this? If you remember 1 or 2 things in 2 weeks from now, I would be so glad. So here's the first one. I already mentioned what happens in the measurement process. I want to kind of explain this a bit more as much as I can. And the strange thing that is happening in the quantum measurement process is that basically you lose information by measuring. I'll explain this a bit further. And the second point is that calculations become complex. The mathematics has a certain complexity, but that part is not specific for quantum. You can, if you kind of want to emphasize it with one short sentence, that is this in red, you see that A times B, this product is not necessarily B times A, which is strange if you think of numbers. 3 times 4, of course, is 4 times 3. And I will explain this also a bit more. So this aspect is very important in quantum physics, but it's also important in other parts of physics. It's more important in mathematics, and I will try to stress these two topics and hope that at least one of them you will remember 2 weeks from now. So observation. Let's start with our normal everyday world. There are many wave phenomena, but there's only one that we can see with our eyes really, and these are water waves. So all our intuition about waves basically comes from water waves. Suppose, it's not a real good water wave, but I wrote there this red. Suppose these red trace is a cross-section through some wave in the Bosporus here. And now, of course, we know if this wave comes by and you happen to have your camera or your mobile phone, you can take a picture and you see the whole wave. So on the camera. Now, in quantum physics, so what we learn is that when you go to the microscopic world, even some things that we thought were particles, they behave like waves, like electrons, but we don't see them. But that's nothing special because we also don't see acoustics, we don't see light waves. I mean, we use light waves. I use light waves to look at you, but I don't see the light wave itself, right? So all our information about the waves other than the water waves is a bit indirect. So in the quantum waves, this wave function is somewhere in some apparatus, which looks, when you open the door and look at the table, it's a bit many devices on the table maybe. And so you cannot see the quantum wave with your eyes, of course, but you have some detectors and maybe some electronics, and eventually you have a display on your computer. And suppose there is a quantum wave in your system and you try to measure this. So suppose this is a wave, let's say it could be an electron wave packet as a function of position, and then you try to measure this. The outcome of this measurement is completely different from this classical picture that we took of water waves on the right-hand side of the slide, because there's all this information in the There's all this information in the wave function, but when you do the measurement, then something happens which in the old days was called collapse of the wave function, but collapse seems to indicate the opposite of an explosion, something that happens as a function of time, but there's no time scale involved in this what's happening in the measurement process. So nowadays people prefer the word projection, because it's a bit more abstract and cleaner mathematically. And this projection happens at a time scale. So far, all experiments show that this projection happens at a time scale as short as the detector allows. You build a faster detector, the projection is faster. Whether this will hold all the way in the future, of course, nobody knows, but so far, this is what we know. Then you repeat the experiment, you get another projection. So this is the randomness associated with quantum physics. The randomness is not in calculating the wave function. This is very deterministic. But when you do a measurement, the wave function gives you the probability distribution for having one or the other outcome. So you repeat this many times, you get different positions, and if you build a histogram, then you begin to see the periodicity. So this is what happens in the measurement process. And I told you people struggle with this. They say why, and they come up with these interpretations. But maybe the best way to deal with this is to say, well, this is how it is. And in gravitation, we also accept there is the force as a fundamental principle. And maybe this is yet just another fundamental principle. So the collapse of the wave function and because you get only like one part of the full wave function when you do the measurement, that's why I said, when you do a measurement of a quantum system, you lose a lot of information that was there. The measurement in quantum physics is this projection onto one of the superposed states. Actually, if you design the measurement such very carefully and to prepare the state very carefully, it can also be that you get a very precise value. For example, if you prepare the system in an eigenstate of energy and you measure energy, then you get exactly that value. Then you don't have this randomness. But normally when the system is in a superposition of the states which the measurement would kind of extract, then you will see only one of them. I was wondering, so first of all, I was about to say that I cannot tell you anything from everyday life which shows you this special feature of the quantum measurement process, that you have lots of information there, but in the measurement you only get out part of this information. But there are some things in everyday life, pictures like this, whereby it has nothing to do with quantum, but it has a similar aspect in that you have more information in the picture than you can see at one time. So you all know this picture. You can see an older or younger lady. Here you can see a vase or two faces, very famous pictures. I'm sure all of you have seen this. But I prefer more abstract. You can also look at this cube in 3D. And because you leave away all the rest of the cube, like the reflection from one front surface, you only draw the edges and you project it in 2D. Now, two different cubes, oriented different in space, have both these projections. So here, can you see the two projections? So to guide your eye, I put them down here. You can see the cube as the left one or the right one. So your mind kind of flips. Of course, so I have to stress this is not quantum, but the aspect that there is more information there than you can see at one time has some similarity. Now, in this case, you can let your brain switch. You can go one from the other. In quantum, this is not the case. Otherwise, it would be easy to extract full information from the quantum system. If you do a measurement and the projection happens, you cannot go back. So it's not quantum. Quantum is really different. But at least this is something, if you have not studied physics and you didn't get familiar with these concepts, this is something that can help you to visualize a little bit what's happening. Now, when you talk about applications of in the quantum world, then I already mentioned the word entanglement, which has then you deal with composite systems, which you can look at one part of the system and another part of the system. And here I put 4 such cubes, and I hope that when you look at them, you always see them always in the same, more or less in the same orientation. This is how your brain, you get used to one and you see all of them. But then in a way, at least for me, when I go through, I see one of them in the same orientation. Then I go back to the first one and suddenly my brain switches and see the first one in a different orientation, but all others also switch. So, I mean, if you want to stick with this imperfect analogy to something that we know from everyday life, you could say it's either all cubes in one direction or in the other. And this is how entangled quantum states would look like. So if you now on so it's a superposition state in this composite system, which is called entanglement because you have very strong correlation. I should say, when you hear with quantum physics, you can build a computer, then you might find this to be strange because we already said if you do a measurement, you look what's the outcome of the calculation of the quantum computer. We have this randomness, and you see this randomness here because if you do a measurement on the first cube, you can either see the first cube in the left part, and the lower line is one orientation, and the right, it would be the other. So both come, if there's equal weight, with 50-50% probability. So this is what you call quantum noise or quantum uncertainty. And why can you hope to do precise measurements? And this is that despite of this uncertainty in the first measurement, if you compare two measurements, you can have extremely strong correlations without any uncertainty. And you can see this here. If you do this first measurement, you will get either of the two cubes. Suppose in this time when we do this, you get the left cube. Then the projection means that you lose the rest. This is the information you lose, right? And you have this. And now, if you have these states, these cubes, if you do a measurement on the third one, it will be exactly correlated. There's zero probability to see this second cube in the other direction if I translate from quantum waves to to these cubes. So that's so this is my first take-home message, that the quantum measurement process, the projection that happens in the quantum measurement process, is of course something you could say weird, but it's, I mean, in many cases, so many labs over the last several decades have seen this effect. Many researchers have seen this many times. So like we have seen gravitation work always the same way. So we basically say maybe we should accept this. And to help your imagination with some guidance, this visualization using these pictures where your brain switches might be a good way to kind of remember this. So in the last slide of this first part, I just want to emphasize that when you do physics, there are many areas where you have more or less high mathematical complexity that applies to quantum physics, but not only to quantum physics. There is, you can have superposition, which you typically always have when you have any wave phenomena, not only quantum waves. And within this, there's also quantum physics with its special projection. So in quantum physics, you have mathematical complexity, you have the superposition states, which is not, both are not unique for quantum, but they apply to quantum. And in addition, you have this projection that happens with the measurement, and that is specifically quantum. Now, I forgot. I wanted to say that when I was in high school, although this was long way back in the last millennium, my teacher told me about wave-particle dualism. And I was always struggling with this a bit because I thought this is really strange. And I think it's because both wave and particle are normal concepts from our daily life. And there is a contradiction, of course, between the two. And this partly contributes to the weirdness of quantum physics, I think. So that's, in the end, I decided I don't like this. I would prefer wave and projection. Projection, we accept there's something new, like in gravitation. At some point, people accepted gravitation. And then this is not such a contradiction. We have a wave, and we have this projection, which is something new. So I think to convey this topic to young people, I'm not young anymore, but I think if I were young, it would appeal to me more. But then you decide for yourself. Okay. This is the first take-home message. Measurement is a projection, and think of this cube. So, second topic, A times B not equal to B times A. This does not apply to numbers. Our numbers, we know we can, we start with natural numbers and we ask questions and we fill the number line all the time until we have these real numbers. Louis, I was always thinking real numbers, should they really be royal numbers? Because they are, I mean, there's no space in between. They really fully fill the number line, but it's just one dimension. So real and royal in Spanish is the same word. So it could be that there's this connection. Now, in classical information theory, in the binary system, we have bits that have either value 1 or 0. So I highlighted them blue, but maybe on this, in the distance, you cannot see this. So 1 and 0 are just two numbers on the number line. So in order to get more numbers on the number line, you need more bits. So if you take 3 bits, then you can have 2 to the 3 numbers. This is 8. So from 0, 1, 2, 3, 4, 5, 6, 7. These 8 numbers you can. So 101 in binary would be the number 5. So you would have more numbers, but they would all be on the number line. Then you have more and more bits. With 10 bits, you can encode the numbers from 0 to 1000 to 2 to the 10 minus 1. And with n bits, you go from 0 to 2 to the n minus 1. But this always stay in this one dimension on the number line. Now in quantum information science, this is different because a quantum bit is not in the state 1, 0 and 1, but it's, you could say, in the state 0, not in the state 0 or 1, but it's in the state 0 and 1. It can be simultaneously in these two positions, in at least two states. So if you think of this as a wave, it's not surprising, because if the wave function tells you a position, and the wave typically, like a water wave, is extended. So for a water wave to be in two different positions at the same time is not a problem. But as in the projection process, we see only one number. Initially, people were thinking, oh, if it's the electron is in this position, fitting the old classical picture that the electron is only a point. And then it's a contradiction to have the electron on the other point. But if you think of the electron as a wave function, this is not really contradiction. And this visualization of this 3D object, which looks like 0 from one side and 1 from the other side, this I took many years ago from a website of Oxford University. And maybe it was Arthur Eckert's group who invented this, I think. So this is the best quotation I could give at the moment. So 0 and 1 means that we are in a superposition. That means we can say we are with a certain weight factor A in state 0, and with a certain weight vector in state 1. And so I can vary this. And you can see even with a single bit, you have many more ways of encoding, because these factors in front, basically, there are as many numbers as you have in the number line. Of course, when it comes to doing the measurement and distinguishing different states from each other, there is some limitation, but there is a whole different world opens up by these additional parameters. And if you not only have one quantum bit, but several quantum bits, suppose you have 3, then you can have superpositions of up to 8 different states. So I just wrote here 3, like the 0, 0, 0 would be 0, 0, 1, 1 would be a 3 in this binary encoding, and the 1, 1, 1 would be the 7, but it could be as many as you want, up to 8. And the factors in front, these are all numbers that you can vary. Of course, the state as a whole should be normalized, so the sum of the modulus square of all of them is a condition that you have to fulfill. So maybe it's if you have 8 such coefficients, maybe 7 you can vary independently. So this shows you that you have many more freedoms, much more freedom when you go from classical bits to quantum bits. And you could say that these quantum bits, they are spanning a higher dimensional space. Each quantum bit is basically like one number line, and then you have 2 and 3 number lines, and we have 3-dimensional space. This is as much as we can imagine. But in mathematics, I'm not sure. There was earlier I saw a mathematician who told me that she had to leave because there's some more important commitment. And somehow mathematicians, they deal with even 10, 100, 1,000 dimensional states. So this is, for our imagination, it's a bit difficult. But this is basically the big difference. And it means that the complexity that you can encode in a system of a few quantum bits is much, much higher than what you can encode in the same number of classical bits. So quantum physics, these are, look at some dynamics in higher dimensional spaces, and higher dimensions, it's really becoming interesting when you go to dimensions higher than 2. And fortunately 3 we can still imagine, because we sit here in 3-dimensional space. And I think all of my colleagues, when we give public talks on the topic, one thing to demonstrate this is by rotation. So if you have a number line, basically you could have some rotation, but only 180-degree rotation from like the number +5, you rotate around 0. By 180 degrees, you go to -5. So plus to -5, you could say, is a rotation. If you have complex numbers and multiply them, then this multiplication of one complex number by another kind of rotates and maybe expands or reduces the first complex number. At least this is a way to look at it. But in a complex plane, when you are in a plane, and if you multiply two complex numbers, you again will be in a plane. So the rotation axis will always be perpendicular to the plane. And as long as you don't change the rotation axis, it doesn't matter whether you first rotate by phi and then by theta, or first by theta and phi. This commutes. But as soon as you go to dimension higher than 2, for example 3, this does not work anymore. So this is a three-dimensional object, and I will now rotate it. And so I will rotate it around a horizontal axis and a vertical axis. So I first do a quarter rotation around the horizontal axis, and then around the vertical axis. And if now there would be water in there, and I squeeze it, and there would be full of water. If I first do the rotation around the vertical axis, and then around the horizontal axis, your precedent will be wet. You agree this is a difference? So it depends on which sequence you do the rotations. What is the output state? What's the effect? And that means you don't have a commutation. A times B is not B times A. So that was the other thing. I hope you can remember, even if you're not from my... Great. So that's not the same. In quantum physics, this is the basis for Heisenberg uncertainty relation. And when you do quantum physics you look at this dynamics in higher dimensional spaces, basically all operations in quantum physics are rotations in higher dimensional spaces. This, in a way, this experiment is very close to quantum physics from a mathematical point of view. And those of you who had who were introduced to vectors in high school, maybe you know about the vector product. This is the vector, the arrows in three-dimensional space, and you multiply two and out comes a new vector. It's the vector product. And we are in 3 dimensions. It should not commute. And yes, 8 cross B is minus B cross A, so they don't commute also. They don't form a mathematical group for some reasons. So there is no mathematical field in 3 dimensions, but you can define this particular multiplication, and also this does not commute. So, okay. So I have a few more slides to expand a bit more on this. This is one thing. This non-commutation is one thing which is important in quantum physics, but basically you have it everywhere when you have waves. And in waves, we say we have conjugate variables like time and frequency, position and momentum, amplitude and phase. And they, with amplitude and phase, one has to be a bit careful because phase has this multiplicity. But in certain limits, this is true. And if you have conjugate variables, you can make one of them very precise at the expense of the other being very broad. So, for example, if you want to have a very well-defined time, like for example you use pulsed laser and try to make the pulse shorter and shorter, you need more and more frequencies in this frequency domain to form these short pulses. And if you want to have just one frequency, you need lots of time and many oscillations to really have a sharp frequency. So that's something special for waves. So it applies to all waves, including quantum physics, but it's not special for quantum physics. But it's important still. And this is another picture to see how when you have two different frequencies or many frequencies in the time domain, you get shorter and shorter. So this can be used in applications. So for example, if you want to measure a certain parameter, and this can be encoded in only one of these conjugate variables, for example, in position or in time, then basically by preparing your quantum state such that the readout system is squeezed in this direction, so it's has a very sharp distribution, then your measurement can be more precise than if you do not use these quantum tricks. So that is then quantum sensing, one of the pillars that was mentioned. I already said that in the projection, because you cannot predict if you have a superposition of two or more possibilities, which of these possibilities will come out in the measurement. So this basically gives you this uncertainty and this noise. But if you have an entangled state, if you measure two, the differential effect of these two is can be almost without noise or without noise. And this is also the reason why you can do quantum computing. I was hinting at this already. So if you have strong correlated subsystems, then you can also have precise results, which can be used also for sensing, but it can also be used for quantum computing. Okay, so the outcome depends on the measurement. So I'll show you now one result from my lab to kind of which fits a bit to this story. And so we work with optics. I'm from the Max Planck Institute for the Science of Light, as you heard. And so if you look at light intensity, you can correlate light intensity. So if you can, for example, if your signal is some light beam, you have a photodetector, and you take a time series, and there is some fluctuation because maybe of some quantum uncertainty in the light beam. And then you have this time series, and then in a computer you could kind of overlap. You could make a copy and overlap with with different relative positions and multiply the two and integrate, and this gives you this correlation function. So this you call the intensity at time t prime times the intensity at time t, and this averaged over all times, this would be the correlation function. So this would be one way to do it, but you could also, maybe because there's that time of the detector, and so the traditional way is more like experiment number 2 on the right-hand side. You first put the light beam on the beam splitter, so you have 2 copies, have 2 detectors, and then you multiply the outcome of the detectors. So this is like a hardwired way to do this intensity correlation, and then you can change the position of this one detector. That also changes the relative time. And so from a classical point of view, you think this should give you the same correlation function, especially if you normalize for intensity. When you do this in the experiment, there is much similarity. So the axis down here, the time is the time difference, t minus t prime, of these for these 2 intensity measures. So as long as t is different from t prime, the 2 experiments give you the same result. But if t is equal to t prime, it's completely different. So this is the trace. This is true for single photons, which not always come. This is sometimes you have a single photon, sometimes you just have vacuum in a stochastic way. Then you see this normally is called anti-bunching in this cross correlation with the right-hand experiment. But if you do the left-hand experiment, you see the same curve, but the 0 time bin has just a big number. And interestingly, so nobody usually was doing this. We now understood that from the difference between the two, you even this can be useful to characterize your system. But from a more fundamental point of view, the difference at the time bin 0 between these two is just the fact that these field operators that are involved don't commute. So the A times B not equal to B times A is a result for this big discrepancy at T equals 0. Okay. So now the final topic is finally, we already mentioned quantum computing a few times. How can this be applied to quantum computing? So let's remind ourselves first how a classical computer works. So you have an input register, an output register, and the input register you put now, I'm not sure, I could have used binary zeros and ones, but now here we have the decimal system, it doesn't matter. So we just have numbers in there. So if you want to do it just with zeros and ones, you have to have a larger input register. And then you use it as input data, and then your calculator, your computer is programmed to do something with this input data and give you an output numbers. And then you put in the output register. And this is the answer to this input. And if you want to get the answer for another input, you have to run the computer again. And if you have 10,000 input numbers, you have to run your computer 10,000 times. In a quantum calculator, remember this big difference between a classical bit and a quantum bit? You can have a series of quantum bits in a superposition of all possible states. I showed you the example of 3 bits, and I showed 3 of them, but I said in principle I could write all 8 down there. This is the same here too. There's no limitation. Even if you have many quantum bits, you can put the input register in a superposition of all possible states. Then you run the quantum calculator once, and in the output register you have a superposition of all possible results. You might say, what a mess. If I look at the output register, I can see anything. I mean, how do I know what I want to know? And the thing is, they are, of course, entangled. They are correlated. So if I measure both of them, what will happen is a projection to one of the possibilities. And now we see the problem. At first, before we did the measurement, a single run of the quantum calculator would create this superposition of all possible inputs correlated with all possible outputs. But as soon as I do a measurement, I project only to one value, which I could also calculate with a classical calculator. So all this parallelism that I had for a brief moment is gone. So this projection is a real problem. Before the measurement, it's massively parallel, and then I lose it all because of this projection. So in a way, you could say I have simultaneously many inputs because I have this superposition. I have all these many results, but when I do a measurement, I lose all but one. It's a different way of writing it down. So if this would be the end of the story, there would not be a hype about quantum computer. So my talk will go on a bit more. So if once you understand at the point when I do a measurement, I will have this projection and I will only get one result. Then maybe you could think, if I need this parallelism not to get many different outputs, but I need these parallel passes to create one output, in this case, you can win. And you could say this is something like a quantum interference. If I want only one output, but to calculate this output, I need all these different passes which interfere to give you this one output, then you can win. And so in a way, this is why I think someone told me yesterday, also at Koç University, you are working on quantum algorithms. Someone, right? And this is the trick. You have to find algorithms for which the quantum computer gives you an advantage. And it's basically, this is the pattern you look for. The first algorithm that really made a difference was Peter Shor's algorithm, which showed that factorizing big numbers, which was assumed to be exponentially difficult, which computer scientists say then this is kind of like impossible, at least if the mantissa is long enough, that this is no longer true in quantum physics. And the algorithm that Peter Shor used, of course, you can also run on a classical computer. And there's one step which is time-consuming on a classical computer, and this is you need to calculate you need to determine the period of a function, which you have to calculate, and for this you need to know the function values to then calculate the period. On a classical computer, there's no other way but to calculate the individual function points. So these would be the function points, one after the other, and then eventually you can determine the period. But in a quantum computer, you have all this information by one run of the quantum computer. And if you, at the moment when you have this input, output register all entangled, everything done. If you now, in the output register, suppose there are all these different function values correlated with the different input values. If you don't do a measurement at this point, if you do, you lose it all. But if you don't do it now, but then you do a quantum Fourier transform, which mathematically is not different from a normal Fourier transform, then you basically have an abstract interferometer, and you go to frequency space. And if you go to frequency space, and this is a period with just one frequency, all the information is just in one bin, and then you can do a measurement, and then you win. So this started the whole field of quantum information science. Peter Shor was around 1990, I think, or something, early 90s. And that, so I think European Union started then in 98 to have the first programs in the direction of quantum information science. This is important because factoring is used in one of the public keys, which now people use. There are other public keys. One should say, though, there has never been a proof that that you could not find an algorithm in a classical computer that could do this efficiently. Only it's not publicly known. I'm not sure. Maybe the CIA has secret information. And then when you read about other keys which are used, then the question is, do we know that it's once you have a quantum computer, you can break the code? Or is there no algorithm known to break the code? So for factoring, it's known, but there are other ways. So basically these public keys, they are using situations where the mathematical calculation in one direction is easy and the opposite direction is difficult. So factoring, the opposite mathematical operation to factoring is multiplication. So for multiplication, we all in school learn very efficient ways to even do it by hand. But the opposite way, we don't know efficient algorithms. And this was based on. But with a quantum computer, you can break it. But there are other mathematical operations which are very asymmetric in their complexity, if you go one way or the other way. And there are some for which we don't know any quantum algorithm yet that can break it. And then they are called post-quantum codes, which are supposedly still secure even once you have a quantum computer. But it's only because nobody found the code yet. So this can change. One has to be careful. Okay. So one obvious application is breaking one of these codes in cryptography. But by now, people know other problems where a quantum computer could help. But keep in mind, it's always situation where you benefit from doing all this massive parallelism, but eventually you're looking for one number. So, for example, pharmaceutical industry is very interested in quantum computing. Why? It's because they deal with huge, big molecules, proteins. They are folded in different ways. This is extremely difficult to calculate, but the geometry of these molecules, how they're arranged, this is closely related to the ground state energy. And the ground state energy is just one value. So with a quantum computer, when you calculate the ground state energy, you can use this massive parallelism. So generally speaking, I mean, another thing is to actually write the algorithm, but maybe you see how this idea goes. And so this, I think, will be true for all these situations where a quantum computer will be much superior to a classical computer. It's where you don't lose this parallelism despite of the fact that your projection gives you only one result. So then I'm close to the end. The applications, we mentioned a few very briefly, range from quantum computer to quantum simulator, quantum sensing, quantum communication. The systems which people look at are very diverse. It goes from superconducting circuits, circuit QED, trapped ions or trapped neutral atoms, semiconductor quantum dots, photonic circuits. These different platforms, all photonic circuits work at room temperature, superconducting at very low temperature. In photonic circuits, it's not so easy to do two quantum gates because you need nonlinear interaction. In other systems with trapped ions, it's much more easy. So these platforms are different from the underlying physics. And so maybe yesterday some of you asked me, some of the students asked me what I think which one of them will win. And of course, I don't know. But I think it could be that there are different applications and some platform is better for one application, another platform better for the other application. Okay, so at the moment we already have large companies, we have startups, we have national projects also in Europe, and so we'll see how this goes. This is a website from the German ministry. I think it's already 2 years old or so. But at that time, they also decided to invest in this direction. So the take-home messages are these two. So I hope 2 weeks from now, if someone asks you, one of them, hopefully you remember, one is this bottle and the rotation, and the other one is these pictures with the cube where your mind can flip. And hopefully this can be helpful in thinking about the topic. Thank you very much.